some white noise. So pretty much a pretty cool, pretty typical experience anyway. This thing is doing its thing. Usually they have a red light. This one doesn't. Oh, well, that's useful. Okay, so let's see here in terms of boring class-related announcements. Your homework was due yesterday. I hope you did it. If you didn't, that's okay, because you get, what, 4 days total? 3 days, 2 days, 4 days? There's some number of days of late days that you are welcome to take for free. After that, you can take more, but it'll cost you, I think, 25% per day additively, not multiplicatively, okay? So your next homework will conservatively be out by, say, the next couple of days. Well, Sebastian and I agree. We got to, come to agreement on how hard a time to give you guys. Cool. Other than that, let's see. When are your project proposals due? No, for a while. You got some time. Oh, next week. Yeah. So get your acts together. Yeah. So typically with the project stuff, I'll be the one grading it. So I'll try when I get your proposals, I'll send some comments back and yeah. Any questions about procedural stuff? This class is pretty straightforward. Homework, project, the usual stuff. Okay. Fabulous. So we're going to pick up where we left off last time, including cleaning up one little theorem that I forgot the proof of because I'm, can't remember anything anymore. And then we'll go from there. Yeah. So to kind of refresh your memory a little bit on what we're up to. First of all, we define the differential of a map, right? So you have a mapping which takes points on one manifold, in our case, manifold is just surface, we're not going to get too fancy here, into points on another, right? And the differential was just the derivative of this thing. And you can think of it like a map from the tangent space of one guy to the tangent space of another. Yep. And just like when we were talking about curves, and now that you guys have done your homework, you're experts on that stuff. Is this thing on? Yeah. We're going to do kind of a similar thing to understand curvature of a surface, basically understanding the angle of the normal vector and how it changes as we move in different directions. Yeah? And that led us to do sort of the natural thing, which was to differentiate the normal vector as a function on our surface. Right? And that's this dn object, and that goes from a map from it's a map from the tangent plane of our surface into what? Itself, exactly. Yeah, so remember the normal vector to our surface is unit length. When I differentiate a unit length thing, we only have like one theorem in this class. Right? When I differentiate a unit length thing and it stays unit length, the derivative has to be perpendicular to the thing itself. And remember that things perpendicular to the normal vector to the surface are tangents. Yeah? And so that was roughly the argument to show that dn goes from tangent space to tangent space. And then just largely out of formality in differential geometry, we defined a second object which is equivalent to dn, right? And this thing was called the second fundamental form. And when I say equivalent, what I mean is that it kind of encodes the same information, right? I could get one from the other, vice versa. So dn, remember, is an operator that takes a vector and outputs a vector. This thing takes two vectors and outputs a number. Yeah, so like if I have a map that goes from x to a times x, where a is a matrix, that would be kind of like the differential of my map. And then here, this would be kind of like x transpose a times y, right? Like that other view of a matrix. And this object is called the second fundamental form. And just to keep you on your toes, by convention, we typically put a minus sign in front of it. Okay. By the way, in this class, like if you make some mistakes on your homework, or if we had an exam, if you made a sign mistake on that, I wouldn't care, because I make a lot of them. Okay, right, and so this object we proved in class. The way that we defined it here, it's got a little bit of a mystery, right? This is differentiating the normal vector and then taking the component in some other direction. And the kind of mysterious property that a few of you guys tried to convince me is natural, and I still don't buy it yet. I'm sorry, Pierre. Is that in fact this thing is symmetric, that if I swap v and w here, I get the same number. Yeah? And this, at least to me, is a little bit unnatural, but just kind of a byproduct of second derivatives commuting. Okay. And then I got myself confused and upset in class, so I thought I'd quickly address a bit of a hole that I left from the last lecture and then continue from there. Right, so the point here is now I'm driving a car along my surface and I'm trying to analyze the force that I experience as the driver. And remember that we took that vector, right, that force that I'm experiencing in the car and decomposed it into two pieces, right? There's the piece that's tangent to the surface and this piece that is orthogonal to the surface. Yeah? And I made a claim, which is that the piece that's orthogonal to the surface is actually just a function of the geometry. It has nothing to do with my driving. Yeah, and then I got confused and tried to prove it and couldn't, and then we moved on. So I thought we'd go back and prove it because I actually have it in my notes this time. I'm sorry I got a little too overconfident with my preparation, and then go from there. Okay, and this is something I'm going to trip over. Okay, so right, so it's basically the object, the theorem we're trying to prove is the following, this thing down here, which is if I take the component, so this actually should be a capital K, remind me, I'll fix it in the slides. This is the curvature vector of my curve, right? So like I'm a car driving PBAL along the surface, right? And this is the second derivative of my motion here. And if I take the dot product, look, this is a little n, so it corresponds to the normal to the surface. That this thing actually is just the second fundamental form evaluated in the tangent direction. Notice that there's nothing here that has to do with my driving. This is just the direction my car is pointing. Yeah, there's a slight difference there. Okay, so now that I have a printout from my Piazza post, we can actually prove it. Okay, so the proof is actually quite straightforward, despite my stupidity here. So the basic point here, remember we only have one trick in like all the things we've proven so far in this class is like to show that the dot product between something and something else is constant and then differentiate it. Right, that's like all we know how to do right now, and then we're gonna just keep doing that. We're gonna do that again, yeah? So that's why I feel like an idiot for not remembering how to prove this. So in this case, there's something that's a little bit strange about the language here. And even this I remembered to warn you about, and then I still got it wrong. And that's that there are two different normal vectors involved, right? Because on the one hand, there's a normal vector to the curve as the car is driving. I'm going to use big N to denote that. I noticed one of many sloppy things in the course notes is I kind of forgot to do that halfway through. You guys should send me, I know there are typos in there, you should tell me if you're actually reading them and you find some. And then there's the normal to the surface, which is little n, yeah? Those are not the same. Cool? Yeah, see some nods? Good. I figured out if I like pause long enough, then you guys will nod so that I keep going, and then I have some confirmation that you're paying attention. Okay, so so quick trivia question here. So what do those two normal vectors have in common? They both have a common enemy, in a sense. The binormal, not quite. I was with you, UA, until the last word there. To the tangent of the curve, right? Because the curve is driving along the surface, so necessarily the tangent of the curve is tangent to the surface, right? So I have two different vectors, big N, which again, big N refers to curve normal, and little n, which is surface normal, might not be the same. In fact, one could be the binormal of the other, I suppose. I don't know what that would do. But anyway, both of those things are perpendicular to the tangent to the curve, yeah? So to derive the Frenet frame, what did we do? We differentiated that relationship, the dot product between the tangent and the normal to motivate the binormal. What do you think we're going to do to motivate this formula? Differentiate that other dot product, that the normal to the surface is orthogonal to the tangent of the curve. Yeah? I'm making these hand gestures as if you guys know which directions correspond to which, but in my mind it makes a lot of sense. Okay, so let's say that I have a curve, gamma of S, he's PB AL, okay? Then I can write down kind of an interesting relationship here. I'm going to abuse notation ever so slightly and say that I'm kind of reading off the normal to, so I'm like driving a car along my surface, and as I do that, I'm reading off the normal to the surface. Yeah, that makes sense? So now I can write down a relationship which formally makes sense, although if you squint at it, you'll get upset, which is as follows. All right, so what is this saying? This is saying the tangent to the curve is always orthogonal to the normal to the surface. Okay, so what are we going to do? We only know how to do one thing in this class. Take the derivative, yeah? Hopefully you're getting used to this by now. Okay, so Derivative of 0 is 0. I think we can all agree on that. So now let's differentiate this guy, right? And so there's a product rule involved. So first of all, what's the derivative of the first term? Well, this thing is gamma prime of S, just gamma double prime. But that has a particular name, right? That is the curvature normal. That's supposed to be a K of S of the curve, right? So that's the dot product with the normal of the surface. So first of all, well, let's finish the formula first. Okay. And then what do I add to that? I add gamma prime of S. This is a heck of a lot easier when I have my notes here. And now what happens when I differentiate this thing in S? So let's think for a second. So this is tracing out a curve along the surface, and I'm differentiating the normal vector in that direction. So this is exactly the definition, in fact, of the differential of the normal. Yeah? So this thing is dot dn in, let's see, it's evaluated at gamma of S. Let's be careful about this. In the gamma prime of S direction. Does that make sense? Okay, so now we're in good shape, yeah? Because, so what is this thing? Yeah, this is just the definition of the second fundamental form, right? Because I took the normal, I differentiated it, and then I dot producted it with something else. There's a plus in front of it, so we have to be a little careful, right? This is minus the second fundamental form evaluated at t twice. Yeah. And what is this thing? Well, this is a unit vector, right? So this is the component of the curvature normal in the surface normal direction, right? So it's exactly what we've defined to be kappa sub m on the board there. And so our proof is done, right? Hopefully I don't have to rewrite this for you. That goes to the other side with the minus. Okay. So that derives the property that we were missing last time. I see it. So let's spend 10 seconds thinking about what this tells us, which is that our car is driving along the surface. He feels force in two directions. One is tangent and one is normal. And the point is that the tangent one has everything to do with the way the driver is turning their steering wheel and nothing to do with the geometry of the surface. And the other one is that the normal component has everything to do with the surface and nothing to do with the way the driver is driving. Yeah, Monday.
Is the kappa up there and the k down there essentially the same thing?
Oh, it is. I've managed to mix notation from 4 different textbooks. I'm sorry. Yeah, this slide requires a little bit of editing. Remind me, I'll fix it. This is what happens, I've taught different versions of this class for many years. Okay. So hopefully now we all agree that indeed this identity is true, marked in green, and life is good. And in particular, that the second fundamental form is really something that's telling me, something about the bendiness of the surface in different directions. And this is the nice way that it relates back to the curvature of a curve. Okay? Fabulous. Notice that, if you step back and think for a second, getting this right, probably 200 years ago when people were doing this for the first time, or 100 or 300, I don't know, Sebastian would know, is remarkably difficult. It's easy to confuse all of these different notions of normal and so on, and you have to get just the right combination to prove these kinds of identities. Okay, so we did manage to prove this thing correctly, and that led us to this definition of principal curvature. The idea being that we can really think of the second fundamental form as a 2x2 matrix, right? It's kind of acting on the tangent plane, right? And we just showed that it's symmetric, and hence it has two eigenvectors in different directions that are orthogonal to one another. So the corresponding eigenvalues are the principal curvatures, and the eigenvectors are the principal directions. And there's lots of nice pictures people draw where you can kind of show that they're wrapping around the surface in nice ways. And so a lot of the early algorithms for surface analysis were basically, step 1 is compute curvature at every point, step 2 is summarize it in some way and do something with it. Right? So for instance, a perfectly reasonable surface descriptor would be take all of the curvature values and just bin them in a histogram and compare two surfaces that way. Yeah? That would certainly distinguish a sphere from a well, not sphere. Hyperbolic, a saddle. That's the word I was looking for. Okay, right. And there are many different visualizations. We already talked about this last time. And finally, we talked about the determinant and trace of that second fundamental form. And those are the Gaussian and mean curvature respectively, at least up to a constant. Cool? Okay, and so that's where we left off last time, is we define these objects, and somehow from a linear algebra perspective, they're totally reasonable things to study. The question is, what do they tell us geometrically? Yeah? And they're totally reasonable things, right? So in particular, we drew this, this picture for the Gaussian curvature. Because remember, the product of the curvature, like the sign of that thing tells you whether the two have the same sign, the K1 and K2, or a different sign. Yeah? So when they have the same sign, your surface is kind of bowl-shaped. When they have different sign, their surface is kind of saddle-shaped, right? Because in one thing, it's pointing up every direction. In the other case, it's pointing up one direction, down the other. Yeah? And so then the question remains, which is, how do you understand mean curvature? And this is a bit of a trickier matter for a lot of reasons, some of which are very subtle. I mean, so if you take a graduate geometry class, you'll spend a lot of time analyzing what is effectively Gaussian curvature. Because in higher dimension, like if you study Riemannian manifold, this thing they call the curvature tensor for a surface is nothing more than just Gaussian curvature multiplied by some crazy object that doesn't matter in 2D. I think that's roughly the right assessment. I'm looking at my mathematician friends. But mean curvature is kind of an interesting beast because it doesn't really make sense in in a vacuum. Like you really need a surface sitting in 3D to talk about it. So there are notions of mean curvature for like a submanifold of a generic manifold, but what you can't do is just talk about the mean curvature of a manifold. Like it needs to be embedded somewhere. Yeah? And the reason is that, like for instance, we talked a little bit about this informal intuition that it's measuring stuff like bending. Yeah? And look what I'm doing to this sheet. This is intrinsically the same manifold. I can crumple it up, and the distances along this thing haven't changed. Yeah? But it's obviously a different shape. This is something that Riemannian geometers often neglect. and in fact, distinguishing these two from each other requires this other number. Yep. So a very simple lemma that you can prove at home, we're not going to bother here, is that mean curvature really is just the mean of the directional curvatures. You can read that directly off of that quadratic relationship that we had before. But the more interesting property is one that we will derive, and this is a little experimental on my part. I don't typically teach this formula because I always get it wrong. Think about the last class where I thought I was getting it right. So we're going to try, and if I get confused, that's just going to be life in the city, okay? But I think it's important because it actually motivates how we're going to discretize this object later. And it's funny, I see a lot. This is probably not surprising to you guys at all, but I spent a lot of time reading through other people's geometry pedagogy, because that's the thing that I have to teach a lot. And almost everybody waves their hands at this particular formula, and I kind of thought, well, that's cheating. Let's just do it. It's not so bad. Yeah? And that's this interpretation of mean curvature in terms of the first variation formula, which conveniently, you guys all just took a first variation on your homework, so you're all experts now. So we're going to do. The good thing is on your homework, I'm not going to make you do higher dimensional ones because those are nasty. But we can do one on the board, and you can watch your instructor get confused as he tries to do it, okay? So before I get confused, let's tell the high-level story first, because that's something I am confident I can do. Okay? So on your homework, what did you show? You showed that if you have a curve, there it is. It's between my hands. You can't see it, but it's there. Yeah? And I want to shorten it. How do I do that? What direction do I move the curve? Exactly, in the opposite direction from the curvature normal. And if you think about it intuitively, that makes some sense, right? If you have a really curled up curve, the best way to undo that is to just kind of flatten it out. And that's roughly what this thing is saying. Yeah? And the question is, does it make sense to talk about that kind of fact about life in the higher dimensional setting? And of course the answer is yes, that's why I'm talking to you today. Yeah? And so that's what we're going to do is sort of speculatively start doing a calculation until I get confused, and then I'll start waving my arms around and telling you how it should have been finished. That sound good? Okay. So here's our basic setup. There's plane. Actually, you know what? We're going to do it on a slidey board so that I can continue a calculation. You nervous yet? Well, that means that I'm anticipating more than one board worth of math. Okay. Man. God, these people. Okay, is there a way to like just dark? There's a way to tell PowerPoint to shut up, right? Aha, okay.
Also you might not want to use that board if you could slide it up. It'll get covered.
No, I think topologically we're okay. These two swap.
Oh, sorry.
Yeah?
I didn't say it swap.
Yeah, so you're right. There is like one of these, you know, like I've got the canoe and there's the wolf and the horse and you got to swap to the two sides of the water kind of scenario. Okay, so there's the plane. I'm debating because I noticed that my notation in our course notes is not optimized for my handwriting on the board, but I'm also nervous to change it live. Oh, hell, what the heck? What's the worst that could happen? So let's say I have the XY plane here. In the notes, it's U and V, but then I use like bold U to mean something else, and that's dangerous. Okay, so there's that thing. And I've got a parameterization, and I'll tell you what T is in a second, into a surface. I only know how to draw one surface. There it is. It's a donut. Maybe here's a point. Maybe there's the origin. So that's where that point goes. And it goes to some neighborhood around that point. I'm not going to worry about things other than that. OK? And now we're all going to do a quick computer animation exercise in our heads, which is we're going to pretend like we take the donut and it starts to like grow in a very small neighborhood around this point. So like my donut maybe like gets a little tumor at this point. Okay? And so the way that I'm going to think about f sub t is like time. Okay? So at t equals 0, it's just my manifold M. And then as my surface evolves, it's still mapping into my manifold M, but maybe sub t. Right? So the thing is evolving in time, and it's just mapping into this thing as it evolves. That makes sense? Okay. So that's our basic setup. Let's add a few more things to this picture. This is where my notation in my notes is going to disagree from what I'm going to draw for you, so this is going to get weird. So for one thing, if I take df dx, I get a tangent vector, right? Df dx, there's a t in there. Yeah? And similarly, if I take df dy, I get a different tangent vector. Yeah? Do these things have to be orthogonal? No. Yeah, they're just vectors. Okay. But later on in this proof, I might assume they're orthogonal if it makes my life easier. I haven't decided yet. Okay. And then finally, there's actually a third vector, which is that like if I'm sitting at this point and I'm just kind of riding the wave as my tumor grows, there's some velocity that I experience. Right, so there's df dx and df dy are like different tangent directions where I'm walking along the surface, but the surface isn't changing. Then there's a third thing, which points maybe off of the surface, right? And that is dft dt. Cool? So those are all the vectors in our problem. Cool so far? Okay. So we're going to call this vector w sub t. Okay? We'll call this thing. Is it going to be confusing for you if yeah, it is. I don't know. So I didn't like my notation before. So what should I call this vector df dy? Any votes? Del of y. Let's stick with one letter. Q. Q sub y. That's a vector. Whatever. And we'll call the third guy Q x. Before I called them bold-faced t, but there's already a t here, and I think that's a bad idea. Okay, fabulous. So these are all the vectors that I could possibly cook up. Okay, and now we're going to do some analysis. So remember, on your homework, what did you do? You took the first variation of arc length. So what would be the kind of analogous thing here? Would be surface area. Yeah. So remember the surface area, at least locally, and this. And in fact, let's pretend like my little tumor is just growing inside of the area that I've parameterized here, so I can kind of ignore what's going on outside of it. Yeah? I'm doing a lot of sloppy things here because I want to avoid having to make all these arguments in differential geometry where you have to patch together a bunch of parameterizations. Okay, so, right, so for now, I'm going to do something shameful, which is I'm going to write an integral without a domain because it's not going to matter. So I'm going to write that the area of this thing as a function of time is equal to what? Well, if I just look at the area of this patch, let's call this patch, I don't know, omega, right? And this region, omega bar. So I'll give you a domain of integration, right? Then what is the surface area of this patch? Well, it's the integral over omega bar of dft dx cross product with df d area. Fine, whatever. Yeah, this is hopefully a formula you remember from calculus class, right? Okay. Is there 1/2 here? I don't think there is. I don't think there is. Okay, right. So this is the area of maybe this little patch of surface, and that's going to be okay because I'm going to assume that my tumor is only growing inside of this patch. So when I take d area, d time, I could have pretended like it was the whole surface and it wouldn't have mattered, right? Because the rest of it is just a constant. Okay, fabulous. So that's what I'm going to do. I'm sorry, I blew my big reveal there. Yeah, so I want to know how area changes as a function of time as my surface is kind of warping a little bit. Yeah? Okay, so let's do this nasty calculation. So, and conveniently now I have 4 boards to work my way through here. Okay, so remember the first thing is that the derivative with respect to time, the integral is with respect to x and y. Yeah, so I can pass one underneath the other. What was that? Is that legal? Yes. Any other questions? No, you're right. There are some conditions you have to check, but generically that's true, and we'll assume that our surface is smooth. Yeah. Okay, this is Houdini's theorem, I think. Yeah. Sure, we'll call it that. Yeah. Okay, so this is d over dt of df dft dy. Cool. So all I did was put d over dt on both sides and apply a theorem that I assert I can use. Okay, right. So now we're going to use another formula which implicitly you guys derived on your homework, right? Which is this is the derivative of the norm of a vector in time. So you guys remember how this works? What you do is you do 1 over the norm times the dot product between this thing and its derivative in time. Okay, we can write that down really quick. So this is d over dt of the norm of a vector, like that, right? This is equal to v of t dot product v prime of t. Like that. This is just like college calculus. You can double check. Okay. Right. So if we apply that formula here, what do we get? Well, we get 1 over this norm. So that's, there's so much writing. dx. T there, the t there. Right, that's 1 over that. Times the dot product between this thing. And in fact, actually, we gave these things names, so let's just use them, right? So this is qx and qy. Yeah. Times the dot product between qx cross qy dot product with the derivative of this thing in time. I know there's a lot of stuff going on all at once, so stop me if you get lost. Yeah. And what is that thing going to be? Well, it's okay. Everybody read that? So this is the product rule composed with this formula here, which you implicitly did on your homework. You might not have noticed, but you did. Everybody with me so far? You should stop me if you're not. Okay. Fabulous. So what have I done so far? I've taken an ugly expression and made it worse. Yeah? So let's continue to do that. So first of all, what is this object? So what did I do? I took 2 tangent vectors, qx and qy, and I took their cross product. What do you know about cross products? There you go, Magnus, right? That's you're either making a rude gesture or you're showing me the answer here. So I got the normal to the surface, or at least A something normal to the surface, and I divided it by its length, conveniently. So this whole thing is just n hat. This is just the normal to the surface. Isn't that handy? Okay. And what we're left with is n hat dot product with this crazy expression here. No. Because this is the normal to the surface, yeah. There are no curves involved here. Sorry. Okay, right. Yeah, and then we have this crazy expression on the right-hand side. So now I'm gonna do a little bit of a sleight of hand here. Okay, so first of all, what did I do? I took the derivative of q in t. Remember that q is the derivative of f in x. I'm going to swap the order of those two derivatives. And then what am I going to get? I get the derivative in x of the derivative of an f in time. Yeah? But I gave that thing a name, right? That thing is w. Yeah? So in particular, this expression, I've got plenty of board space. See, I did it right. Topological Blackboard challenges are an issue in my everyday life. Okay, so this thing is n hat dot product with this parenthesized thing, and this is really dw dx dot product qy. What's that? Cross, sorry. Plus qx cross product dy. Cool? Notice we're doing all kinds of sneaky tricks. We're just like basically rearranging stuff all the time. Yeah? Okay. Fabulous. We're halfway through my notes. Okay, so now we're going to use yet another identity you probably forgot from pre-calculus class. I'll put it in our table of things you forgot over here, which is the triple product identity. How many of us remember this guy? So this is A dot product B cross C. Yeah? Wow. Get excited, guys. No more groans, for heaven's sake. What on earth? Lord. So this is B dot product C cross A. If you can't remember that, the easiest way to remember is it can cyclically permute, but it can't flip backward. Yeah? Because it looks like a determinant. Okay. Well, take a look. So I have this, dot product that, cross that. Smile. Jesus Christ. Okay. So we're gonna apply the cyclic permutation rule, and what do we get here? Well, we get that this is the double integral of. Okay. So now we're gonna move this guy to the outside. Okay. So we're gonna get dwt dx dot product with, and now this guy will be next, right? So it'll be qy cross product n hat. I'm translating my notation live here, so you should catch me if I make a mistake. And similarly, here you get dwt dy dot product with n. Yeah, that's me. Okay. Cool? Oh, did I get it backward? No, I don't make mistakes. No, this is right. Because I had to move this guy 2 guys to the left. Right? So when he cycled around, he ended up first. Yeah. Yeah. Okay, so now, continuing to apply, this is basically just an excuse to apply all the formulas that you forgot from calculus class. Don't look like that, Sebastian. This is right. No, okay, so let's say that I have a function in a domain, in a vector field. There's my domain. And I look at the following quantity, which is the integral of the gradient of my function dot product with my vector field over my domain, omega. I told you this is going to use all the things that we don't like to use. And furthermore, let's assume that f and v, just for laziness, restricted to the boundary of the domain, are 0. Okay? So anytime you see a formula like this in this class, this should be like screaming out to you, because I have derivative of one thing times another, and there's like only one thing we know how to do, which is integrate by parts. That comes by many names. It's Stokes' theorem, Green's theorem, divergence theorem. What are some other ones? What was that? Divergence theorem. I don't know. Curl theorem is probably a thing. Whatever. Right. So and remember the way that we do it is we flip the sign, we move the derivative, and we fill in dot products where we need to until it makes sense. Yeah? So let's do that real quick. So there's no boundary term because I was lazy. Yeah? And what I'm left with, well, if I move a gradient in front of a vector field, that better become divergence. And so that becomes your formula. This is just a way to remember it. I mean, the real way to do it is to look up, the divergence theorem or Green's theorem, right? Okay. Yes? No. I had a friend in college that used to always say, like, I think I'm right. No, I think this is right. So the way to remember it, so you can always, you read cyclically, right? So in this case, I'm going to read this guy, then that guy, then that guy. So I always read it in this order. Alternatively, just get a piece of scrap paper out and check. You'll see that this is right. Okay. Fabulous. Okay. So this is our divergence theorem. And now let's take a look at our expression here. And this is where I actually, when I was writing this proof, I got a little caught up. Because take a look at what's going on. So W is a vector, but let's say that we forgot that for a second. Then look at these two terms that I have here. This is dw dx and dw dy. So that looks an awful lot like the gradient of W, right? And then I'm kind of taking the dot product of this thing. I know this is a vector, so it's not really a dot product. It's more like a matrix vector product. But if I forgot that for a second, right, this is getting multiplied by some other thing. So this is really like 3 instances of the expression on the left-hand side. Do you see that? And so if I integrate, and this is where I'm going to let you guys convince yourself a little bit of this at home. There's a little paragraph justifying it in the course notes. But in effect, it's just an application of the formula on your right here. I can write this in a different way. What's certainly true is there's a minus there because we integrated by parts. Right? Remember that I assumed that basically all interesting things happen inside of our little patch, so I can ignore boundary terms. See how it's sneaky like that? Okay, so what's going to end up happening? Well, the gradient in x and y is going to come off of W and go kind of onto this other term here, right? And so what you end up with at the end of the day, and this does require some justification, which I encourage you to do at home, is the following, which I'm also translating from my bad notation here, TV, which in our notation is QY, cross N of N. There we go. So let's sit for a second and bond with this spiritually, okay? So what just happened? I took the gradient off of the W and I moved it onto the other term. I used to have something that looked like a dot product with a gradient, right? Because I have 2 components, they're multiplied and summed. And now I have something that looks kind of like divergence. See, there's d over dx of something plus d over dy times something else. So hopefully you can kind of intuitively see where this is coming from. And I'll let you go home and convince yourself that if you wrote this in components like x, y, and z, or I guess just x and y here, that this is actually the formula you would get. But it's basically just a souped up version of what's on the right-hand side there. Okay, so I totally lost you guys yet? I'm trying. Okay, fabulous. So, right. So let's, what do you think we're going to do next? Well, we have a derivative sitting in front of a product, so we might as well, expand that out. And what are we going to get? Something kind of magical happens. I keep saying that today. So this is minus the double integral WT. Okay, so let's say that I swap the order. Now I'm going to put, and this is why I know that my sign was right, because otherwise this step would be wrong. I can swap the order of these two guys and make this Q of x cross product with n hat and put a minus there, right? Okay, so why would I do that? Well, let's do something sneaky. Let's say, okay, so we're going to get one of the terms in the product rule here is going to be Q, Y, cross product, dn hat dx. You should be like getting excited. Look what just happened there. Do we know what that is? That looks an awful lot like the second fundamental form, yeah? Yeah? Okay, and similarly we could write the corresponding term in the other guy, right? So this would be minus Q, oh, I'm sorry, x cross dy. Yeah? What happens to the other two terms? They cancel out. They die. Thanks. Yes, you're absolutely right. The other two terms cancel because they're the same for both. Yeah? And now we're starting to be in good shape. Okay? So let's write this in slightly different notation to be a little more suggestive, just for fun. Yeah? So in particular, this thing is minus a double integral of WT. Right, so what did I do here? dn du. Yeah. Okay, so this is qy cross product with dn evaluated in the qx direction. Yeah, this is just notation for the same thing. And similarly, this is minus qx cross product with dn hat evaluated in the q. Now it's starting to look like a fundamental form, yeah? Okay, so let's think about this. I'm using this phrase a lot today. Let's think about this expression for a minute. What direction? So, okay, W is kind of arbitrary, right? Like this is the direction where I was bumping the surface. Notice that this is starting to look an awful lot like when we took variational derivatives. We kind of factored out the direction we were differentiating in and then got some other expression next to it. Right? That was like you went to all this work. We notice we followed exactly the same outline, right? We integrated by parts, we differentiated under the integral, and now we have a third thing, which is we've isolated W. We've gotten to a lot of work to isolate the motion of my surface. And now we have this other thing, and our question is, what the heck is this thing? Yeah? Okay, so first of all, what direction is this not in? The normal direction. Yeah? Sorry, that's a weird way to put it. This is a tangent vector. Yeah? What's the cross product of two tangent vectors? The normal. How about these two guys? Oh my God. Right? So what just happened? This whole time we took the first variation of surface area, we got a direction parallel to the surface normal. That's kind of what we wanted, yeah? By the way, why does that make sense? Let's think intuitively for a second. It's easy to get lost in all these symbols. Why should it be when I take the gradient of surface area, I get something parallel to normal? Indeed, it's natural. It's only right. But let's think geometrically for a second. What happens to a surface? What happens to the area of a surface if I slide the surface along itself? Nothing. Right? So if I want to change surface area, I better move it in the normal direction. And thankfully, calculus agrees with me. Okay. So because of that, we're going to do one more sleight of hand. And this is where I don't have it in my notes. So we're going to see if I manage to get it right. Do I want to do this? Sure. Okay. In fact, here's a case where we're going to maybe make one additional assumption to make my life easier, and then you guys can check it at home. Okay? Right. So let's see here. Because it's in the normal direction, I can do something kind of sneaky. I can write this as minus the double integral of WT dot product with n, which is the direction of my vector, times a scalar, which is n, again, dot product with all this other stuff. You see that? Because this is the component of this in the n direction. But we already know it's in the n direction, so I just kind of like wrote it twice. And so the question is what is this object? Any guess, by the way, given like what we started with 20 minutes ago? Wrong. It's mean curvature times 2. Yeah. Okay. So and what do you think we're going to use to prove it? Triple product identity. Yeah, because take a look at what happened. We have n hat dot product with qy cross product with dn hat in the qx direction plus minus qx cross product dn hat in the qy direction, right? That's our expression so far. And like in some sense at this point we already kind of know where we're trying to go, or trying to make it look like mean curvature. And we know, what does mean curvature look like? It looks kind of like, you know, dn dot product with something. We don't have that right now. Yeah, so we're going to keep cycling it around until we do. Yeah. Okay, so in particular, what can we do? Let's cycle this expression to the left. Yeah, so I get d n hat and the qx direction, dot product with, this is where I'm likely to make a mistake. Well, this and all the other places. Qy, I think I did it right. Minus dn of qy dot product with n cross qx. Yeah? And finally, we can write this in notation that we know and love, right? Because I'm getting good at this. Okay. What is this thing? Well, this is the second fundamental form minus, right, because there's no minus in the first term. Yeah? Evaluated, well, it's symmetric, I don't really remember, but whatever. It's qx and then n hat cross qy, right? This is just by definition. Yeah? And similarly, we have Maya plus the second fundamental form in qy n hat cross qx. Yep. Qy. Okay. I'm going off book now, so there's even more probability of a mistake. But like I left it as an exercise in these things, and then I thought this is kind of a hard exercise, so I should do it in front of class. But then I remembered that I'm bad at math. Okay, so I claim that this thing is 2 times the mean curvature. Okay, so how can we see that? And this is where I'll do a version of it, and then you guys can convince yourself of the more general version. You know, whenever professors say that, it's because they were looking at their notes and they realized they couldn't do the general one, just if you're wondering. So in particular, we're going to assume that qx is orthogonal to qy. Okay, that's actually kind of okay here. One thing you can convince yourself is there always exists a parametrization where this is true. But you really should be able to prove it for the general case. I'll let you do that at home. I know this is true because I listed it from an exercise in another book. Okay, so in that case, let's draw a picture of what's going on. So the blackboard is the tangent plane. The normal is all of you, right? So here's qx, here's qy, and then n is like that. Okay, so what is n cross qy? Everybody raise your right hand. Yeah, so if you have n and you grab onto qy, you get minus qx. Yeah? Is that magic? Okay, what about n cross qx? So now we take your right hand, you do that. Oh boy, I can never get it right. And you get qy. Okay. Not gonna lie, I just read that here and then pointed my thumb there and it worked out. Okay. We'll take a look. That's exactly the trace of the second fundamental form. And we're done. Yeah, so this is 2 times mean curvature. Whew. All right. So let's step back like 50 feet and see what we just did. Okay. I think we managed to do that without any major math mistake. This is a good day for me. Okay, so you guys are all going to post on Piazza tonight about why this is completely broken from step 1. Okay, so right, what did I do? I took a surface and then I said, okay, let's say my surface is evolving a little bit in time and I want to know the rate of change of surface area. Yeah? What we showed is that that's equal to the component of the motion that's parallel to the normal scaled by mean curvature. Yeah? That's what we proved at the end of the day. Right, that's this formula here where all this bracketed thing we just showed is mean curvature. Yeah? So what does that tell us? That tells us, let's say I want to do gradient descent. We're going to flip it backward, right? Like remember the argument you made in your homework, right? You did a similar calculation for the length of a curve. Then if you want to do gradient descent, effectively what you do is you flow along this thing that gets dot producted there, right? That's this notion of directional derivative. Yeah? So in this case, what is it saying? It's saying if I want to decrease surface area the most, how do I do it? I go down minus the mean curvature normal. Cool? So let's take a sheet of paper and let's bend it a little bit because otherwise it doesn't have mean curvature. Where does minus the mean curvature normal point? Well, down from the top, in from the sides, like kind of like that. And that makes sense, right? Because if I take a cylinder and I want to decrease its area, what should I do? I should just flow it toward its center until it turns into a straight line. Yeah? And that's basically what we just showed. Yeah? By the way, I got a question at the end of the class, which is great because it demonstrated a lack of understanding that I wanted you to have. Which is, if I do mean curvature on this sheet of paper, what does it mean curvature flow? What does it not do? It doesn't unfold, which is somehow the people's intuition. That's not what happens. Instead, it shrinks in on itself. It wants to decrease surface area. Unfolding doesn't change surface area. What does unfolding want to do? It wants mean curvature to be 0. This wants mean curvature to be negative. It wants to be as negative as possible. Yeah? That's why minimal surfaces always have negative curvature, or non-positive at least. So that's the difference, yeah? So we could do this whole calculation for mean curvature squared, and that would be a very fancy geometric flow called Willmore flow. This thing, unsurprisingly, is called mean curvature flow, and it's actually used quite a bit. So I think we're still debating whether to put it on your homework or not. But one of the most famous algorithms in triangle mesh processing basically just does gradient descent along the mean curvature normal. And what this does, it takes a noisy surface and it makes it into a smooth one, because the best way to decrease surface area locally is kind of coincides with the best way to smooth the surface out. Which makes sense, right? If the surface is bumpy, the mean curvature flow kind of counteracts that. Okay. Isn't that exciting? I've never seen a college class that actually proves this formula, and it's a handy one. So we're not going to prove all these, like, enough already. So you could ask a question which is like, well, what does Gaussian curvature mean? Like, can I interpret it in terms of areas and angles and things? The answer is yes. These are more difficult formulas to derive, but we'll show a discrete version of one of these next time. Oops. Okay, so and these are sometimes called comparison formulas. So let's take a look at this picture here. And this formula is cheating a little bit because we haven't defined distance yet, but we're going to use it. That's why we're not going to derive it. But I think it's kind of intuitive what's going on. So the point is, let's say I'm standing at this circle and I walk along the surface 1 inch. Yeah? And that inch is in geodesic distance. So it's like I have a measuring tape behind me and it's unfurling as I walk along the surface. Okay? I can draw a whole kind of unit circle by going all the different directions out of that center point, right? And I can ask for the area of the circle enclosed in that radius. Does that make sense, that picture? Okay. So, right, so let's look at the second formula first. So R here, I knew that was going to happen, is the distance out that I walk. Right? And then I compute two numbers and I compare them. One is pi r squared. What is that number? Area of a circle, yeah? And this thing is the area enclosed by this loop. And I can compare the two. I can subtract them, maybe normalized by a particular thing here. And what ends up happening? Well, what you actually get is Gaussian curvature. Right? So one way to think about Gaussian curvature is a sort of like excess area. Right? So take a look at this point. This is a positively, in fact, whoever drew this figure that I stole from the internet did a great job. Because if you look at this little loop, what do you see? There's a lot of area. It's kind of like I took a piece of cloth and I pulled it through this ring, right? Relative to like the same radius on a flat sheet. And that's the point. This is a totally reasonable way to think of Gauss curvature, is for an itty-bitty little ring around a circle, or around a point, how much extra area do I have relative to a flat circle? Yeah? You could ask a slightly different question, which is, okay, let's look at the locus of all points that are radius r away from the center point. In some sense, you could call that a circle. But here's the thing. I just defined this object. It's not necessarily a circle on a curved surface, right? It's like a potato chip thing if I'm on a negatively curved surface. And so I can say C of r is what I'm going to call the circumference, which is like the arc length of whatever I get when I take the locus of all points that's radius r away from the center. Yeah? So 2 pi r is what? It's the circumference of a circle. I hope we all agree. Right? C of r is just whatever I get if I'm an ant and I have a piece of string that's attached to this point and now I like walk around the maypole here. And the comparison between those two also gives you Gauss curvature. Yeah? So anyway, this is an extremely intuitive quantity. The point that I'm trying to drive home here, which I think gets lost in a lot of geometry classes, is that these are totally geometric objects. This isn't just some thing you got from calculus class. Like, you can talk about Gaussian mean curvature without any reference to calculus at all, by just drawing circles and measuring areas and things. Yep. So in some sense, this is really a nice extension of, like, you know, if you were back in the BC times and you were doing all of your geometry with ruler and, well, not with a ruler, with a straight edge and a compass. Yeah. This is some extension of that philosophy. That's why, like, when you go into undergrad geometry books and, like, the first thing they do is they take a parameterization and then they define curvature that way, I think that's totally cheap. Like, really, this is the definition you should be thinking about, right? Because this is the one that's telling you, like, geometrically what is curvature. Okay, so anyway, I'll get off my soapbox. One question you might ask, remember we kind of talked about the fundamental theorem of curves before, that if you know curvature and torsion functions, then you know the curve, right? You can reconstruct. There's a similar picture in geometry of surfaces, but it's a little more complicated to state. We're actually not going to dwell on it much in this class. The easy thing to say is if you have a map that preserves just Gaussian curvature, that map is an isometry, it preserves distances. But remember that the map from this surface to that surface is an isometry, so it's clearly not the same as a rigid motion. Yeah? So if you have a map that preserves the first and second fundamental forms, remember the first fundamental form is just dot product. Second fundamental form is basically mean and Gaussian curvature. If you preserve both of those guys, you're necessarily a rigid motion, like a rotation, a translation, and possibly inversion. The gotcha in this theory, and this is why, like, this shows up at the end of your undergrad class if you take it, is that there's a set of equations called the Gauss-Codazzi minority equations, which says that not all fundamental forms can be used to make a surface. And this is the difference from the curve case. Remember, in the curve case we showed you can cook up any curvature and torsion function and then just cook up a curve with that curvature and torsion. This is saying that there's a certain compatibility condition you have to check before you can do that for surfaces. Yeah? So anyway, we're not going to dwell on that. It's not terribly important for the applications that we care about. But the high level point, the who cares here, is that curvature really is kind of determining local surface geometry. And that's the sort of the high level thing to think about. And that's really what motivates the kind of applications that people have in practice, right? So here's just to name about 300 of them really fast. Because these are really, as computer scientists, I think you guys are actually much better equipped to just look at these pictures and probably fill in the algorithm, given a way to compute curvature. None of these things is terribly complicated, right? All these algorithms are compute curvature using some complicated thing and then do some small derived calculation after. Yeah? So a very simple one is to use it as a descriptor. Descriptor is a term that will show up in a lot of this class. This is the idea that it is describing the geometry near a point in a surface. So let's say that I have two different 3D scans of this dragon. Maybe they're just rigid motions of one another, but it's still not clear if I choose a vertex here where that is on the other surface, because maybe they're slightly deformed and noisy samples of one another. Well, what do I know? I know that if I want the point corresponding to his tongue here, yeah, I compute the Gaussian mean curvature. I can kind of narrow down my search on the other guy by looking for just points with similar Gaussian mean curvature. Yeah? And later on, when we talk about the heat kernel, we'll see that's basically the state-of-the-art strategy for surface mapping is to come up with lots of numbers that would be the same in your mapping, and then just try to find things that match. Yeah? Another one is in smoothing and reconstruction. So mean curvature flow is the standard algorithm for smoothing out a surface. We'll have you implemented at some point. Other types of algorithms will, like, there's actually some notion by which you can have a discrete version of Gauss-Codazzi equation. I should be careful, this is filmed. I don't totally buy some aspects in this research, but it's interesting stuff. More importantly, some people use it to measure fairness. Fairness here is not, our research group also works on political redistricting. That's a very different type of fairness. Here we mean smoothness of a surface. So if you take a look at these noisy versions of this weird surface, this is, by the way, in our pantheon of 3D models. This is another one that shows up a lot in computer graphics world. Anybody know what this thing is called? It's called a fan disk. Anybody know what it does? I don't either, so I don't know. It's some 3D scan of a mechanical part. You know, if you're trying to kind of understand how noisy your mesh is, then maybe you measure its curvature, and if you want to denoise it, maybe you try to reduce the curvature. Yeah? This actually is a great example of where that can go wrong, right? Because if you take a look on these sharp edges, curvature isn't well defined there, right? And so these algorithms end up failing and actually adding artifacts where you didn't have them before, which isn't so great. One of the most popular ones, at least in the kind of 2000 to 2010 era, was in the world of non-photorealistic rendering. So in non-photorealistic rendering, the point, which I think has been lost a little bit in modern computer graphics literature, but is a fun thing to think about, is like we spend a lot of time talking about rendering algorithms that simulate light, but like, why bother? I mean, there are like all kinds of ways to communicate a shape, right? And there are all kinds of perceptual studies that say that your eyes, your brain, or your nose, your teeth, whatever, sense principal curvatures and use them as a cue to understand shape, right? All of us are looking at, well, two different two-dimensional signals, but inferring some pretty complex three-dimensional information. And there are a lot of, some of these studies are believable, some of them are a little bit high-level things that are talking about how artists, like for instance, if I ask you to cross-hatch a surface in a way that captures its detail, right? You likely will cross-hatch in directions that are roughly parallel to principal directions, which makes some sense because those are the kind of interesting curvature directions, right? And in fact, if you read, what's the famous German word here? It's not Ansatz, that's the other one. Gestalt, whatever kind of discussion. There's a lot of talking about principal curvature and direction and so on to identify interesting curves on surfaces to render. And so a lot of the algorithms for kind of finding interesting lines to draw and so on, the very first thing they do is compute principal curvature direction and then use them to guide some kind of stroke, procedure. Another one that actually continues to be a pretty modern theme, including one in my own research group, is to guide meshing. This is one of these chicken and egg problems, which for some reason usually perturbs physicists when I talk about it in their department. We have a mesh, which is this hand here, but oftentimes you want a different mesh, like this quad mesh on the right-hand side, right? So for instance, artists like to work with quads a lot. And there's a problem then, which is I have a 3D surface, and I want to tile it with like little quadrilateral shapes. And so a very typical way to do that is to compute some kind of vector frame field, like some perpendicular directions that have something to do with the geometry of the surface, and then kind of extract these things as the flow lines of those fields, right? And so a lot of work goes into designing these things so that that mesh ends up looking nice. This is a problem we know a lot about in my research group. You should go talk to my grad students. And some of the earliest methods for doing that, such as this thing from Pierre Allier, do that by just computing principal directions and then extracting the mesh parallel to those. And arguably most of the modern algorithms more or less still do that, although with some hacks to make these things more integrable. Right? Notice that he actually failed at quad meshing. I mean, take a look. There's a degree 5 object there. Right? So the weird question to think about when you work on these problems, which is one that like I just spent all morning arguing about, is on what conditions on this field am I likely to extract a pattern over here that actually looks like a grid? Yeah? That's a hard problem. That's a topology problem. Okay. And of course, this is a special topic for me. Actually, my first patent was on a method for computing curvature and using it to segment a surface. This algorithm is completely out of date and useless. But the kind of fun thing is actually this patent, when you write patents, they ask you to like make the most general claims possible, and they say, oh, it's the patent office's job to narrow it down. And so I'm pretty sure I have a patent on Gaussian curvature if you read this thing. So I expect my royalties when you do your homework. Okay, so now let's talk about meshes, and obviously we'll just get started today, and then we'll finish up next time. As usual, I'm running behind, but that's life. And it's a good thing, because this class moves too fast. Okay, so just like before, remember we got all upset that we computed all this beautiful theory of curvature on curves, and then it was all completely irrelevant because curves are flat in the discrete case, right? Just a bunch of line segments, and what does a man to do? Yeah? And so essentially we're going to follow exactly the same pattern here. Here's our favorite dolphin. This is not a member of the pantheon of triangle meshes, except that it's the one thing that's rendered it on Wikipedia, so you see it in a lot of talks. But in any event, this dolphin is piecewise flat. He does not have, or she does not have interesting curvature, except at the edges and the vertices, where your curvature is like a little too interesting, right? It's infinity. Yeah? In fact, to make matters even more complicated, I would argue this thing does have Gaussian curvature along the edges and that it's still 0, right? Because I can unfold the two triangles into a flat object without changing distances. Yeah? So this is a weird object, right? Already a lot of funny things have happened. Gaussian curvature is somehow kind of sitting on vertices. Mean curvature, which is this hinging motion, is kind of sitting on edges. Yeah? And the question is, can we operationalize that? And the answer is yes. There are many ways to do it. So we'll start with kind of a heuristic algorithm that is sort of representative of what we used to do in this field. And then I guess in our next lecture, we'll start to fill in the details of the discrete differential geometry kind of conserved quantity approach to the same problem. Okay? Okay, so the standard citation for computing curvature goes to Gabriel Tobin, who, oh, look at that, I didn't actually realize that. He was at IBM Watson, so he has a very close connection to IBM, who are now our neighbors here at MIT. Actually, I think now he's a professor at Brown, is that right? Oh. In any event, this is the sort of standard method for poorly computing curvature on a triangle mesh. And then there were many algorithms that came after to do it better. But he's the first. And the reason that I chose it is that it really is representative of this kind of cottage industry of research papers in geometry field in the 90s and early 2000s, where you would take your favorite formula for curvature, whether it was variation of surface area or taking the directional derivative of the normal vector or whatever, and you'd kind of do some divided differences approximation of this thing, and you'd call that your discrete curvature, and you're done. And it's true that many of these things all agree to first order, and it's very hard to say anything about any of them. But it's good to be aware because these algorithms are out there in nature, and they're things that people use. Yeah. So in Tobin's case, he did kind of an interesting, weird move, which I wouldn't have guessed, but it turns out to be a handy formula. So he showed the following. This was on the homework in previous versions of this class. I think it might be useful to have it in this one too. We should talk. Which is, he said, okay, let's grab a point on a surface. I'm going to find t theta. So I'll just randomly choose a reference theta. It doesn't matter here because I'm going to integrate from 0 to 2 pi. Yeah? And t theta is the tangent in the theta direction. Notice none of this stuff extends to 3 manifolds, by the way, for the physicists that were asking about that. And now I'm going to take the outer product of t theta and itself. So if t is a 3 vector, then what is this object? 3 by 3 matrix. What's its rank, just for fun? It's rank 1, right? Because I wrote it, I factored it for you. Okay. I'm going to scale that by the curvature in the theta direction and then average. This is kind of like a covariance in some very rough way, except these things can go negative, so that's not entirely true. Okay. And one thing that you can prove here, just by basically plugging in, like we know kappa sub theta, right? We already kind of showed these formulas. T theta is just, this is how you draw a circle, yeah? Okay, so, right, so one thing you can show, first of all, can anybody name an eigenvector of this matrix with eigenvalue 0? There's like only one vector I haven't talked about at point P that should show up. The normal, yeah? Right, because when I multiply, let's say I put n on the outside, n has no theta dependence, so I can move it here. Now I have t transpose times n, right? T is tangent, n's normal, its dot product is 0. Can anybody name the other 2 eigenvectors of this matrix? The principal directions. You happen to be right. However, if you look at the eigenvalues, you'll see it's actually kind of funny what happens. You get 3/8 times the minimum curvature plus 1/8 times the max, and vice versa. And I think this is a good thing for you guys to check at home. We'll throw it on your homework. Yeah? Because it's basically just an extension of the similar kind of arguments we've already done. Okay, so in any event, we now have a grasp onto some formula that we can discretize, yeah? And that's what we were after. So we got it, yeah? We got it, folks. Okay, so what does Tobin do? He says, well, that's an integral. We don't like doing integrals, so let's replace it with a sum. So instead, we're going to just generate a bunch of tangent directions out of a given vertex on a mesh and try to construct this matrix, yeah? So what ingredients do I need to be able to do that? Well, for one, I need a tangent direction, yeah? For another, I need a weight, right? When I take the integral, I got to sum up. And then finally, I need an estimate of curvature. Yeah? Those are our 3 ingredients. And we're just going to do them all kind of a little bit off the top of our heads, yeah? Okay, so first of all, I'm at a vertex on a mesh. So these are easy calculations, finally. What's a reasonable probability? So if let's see, did I call my center vertex V or U here? Actually, totally unclear. U, so the picture you should have in mind Here's a vertex on my mesh. Here are his neighbors. The center guy is V. His neighbor is U. Right, so there are a bunch of tangent-ish directions here, right, which are just the edges. Not clear if those really are tangent directions. That's something we should come back to, but yeah, in Tobin's case they are. Yeah? Okay, and the question is, okay, so what ingredients do I need? Well, I got the tangent directions, just the difference of these divided by their norm. Yeah? So I need a curvature in that direction and a weight. Yeah? So let's start with the curvature piece. This is not so bad. So, what do you think I'm going to do? I'm going to take a curve gamma of S. I'm going to take him to be parameterized by arc length. Don't all speak at once. Okay. So right, and in particular, I'm going to say that gamma of 0 is the point that we care about. I guess V here. Okay. So now I'm going to draw a curve. We're going to pretend like this is a smooth surface for a few minutes. And then we're going to squint and plug it into this formula, because that's what Tobin did. There's no, like, this is just a divided difference kind of approximation going on here. Okay? Right. So let's do a Taylor series. What is gamma of S minus V? Well, so this is the 0th order term, my Taylor series. Yeah? So then I can add the tangent at 0 times S plus 1/2 times the curvature of the curve gamma. Let's be clear here. At 0 times the normal at 0 times S squared plus big O of S cubed. Okay, that's just because like we've basically defined these things to be the first and second derivative of the curve. So this is the Taylor series. Yeah. So there are two corollaries that we can write from this. First of all, let's take the norm of this expression squared. Okay. So, well, what happens? I take the dot product of this thing in itself. What's the dot product of t of 0 in itself? What is t? T is a unit tangent. So at t dot t is 1. Yeah? So I get, yeah? And then I'm lazy. You notice that everything else is higher order? Cool. Okay. And similarly, I can take 2 times the normal at 0, dot product with this expression. Okay. What's the normal of the curve dot with t? 0. Thank you. Okay. In fact, actually, I'm sorry, I'm going to take the surface normal. Oh boy. What's the surface normal dotted with t? Still 0? Why did I do that? Well, now we know what is this entire expression, the curvature normal dot product with the surface normal. This is the directional curvature of the surface in the t direction. Remember, that was the formula that I screwed up in our last lecture. Okay, right. So let's write that as kappa sub. We'll put the theta here, right? And again. Okay. So what do? Well, I can solve for the curvature in the theta direction, right? By just kind of taking the ratio of these two things, right? Because notice I have kappa theta s squared divided by s squared plus a bunch of terms I don't care about. Yeah. So when I do that, I get the following approximation, which is the norm of that thing squared plus, and okay, so if you keep track of your big O's, you'll see that you get an order of S left over. Okay, I'm hurrying because I don't want to spend 2 lectures going over this boring algorithm. Okay, so all I did was just divide these two expressions and notice that there's a kappa there and not a kappa there. Okay, fabulous. Okay. So what do you think Tobin does? He says, okay, great. So I have an expression for finding some approximation of curvature plus some thing that vanishes as my mesh gets refined. I'm just going to do that and make this approximate. Okay? And now I have a way to take sort of the curvature of a surface in some direction. Because take a look at what this expression is doing. This is the normal at say, the center vertex. This is the thing that I have on hand. This is the kind of the difference between 2 points. It's kind of like the difference between u and v. Yeah? And similarly, that's what's inside of this norm. So these are like all things that I can kind of compute on a mesh. Yeah?
How do we have the normal on hand?
Oh, because we guesstimated that ahead of time.
Okay.
Yeah, so you're right, that a per vertex normal on a triangle mesh, you caught me, is a tricky object. So what Tobin does is he takes all the triangle normals adjacent to a vertex and averages them and divides by the norm. Yeah. It's actually a reasonable approximation, turns out. By the way, where does that approximation break down? Well, if you have two triangles like that, right, and you average, you get 0. Yeah? Okay. Right, and so that's the expression you get for curvature. And then for a weight, for an edge, I told you this was heuristic. I take half of the area of this triangle plus half of the area of that triangle. That's a reasonable weight. It's kind of roughly the amount of stuff that's adjacent to that edge. Yeah? And that is his final expression. Yeah? So what he does is he sums over all the vertices adjacent to the center guy. He plugs in this expression for curvature, where this difference is just the difference between the neighboring vertex and the current one. Yeah? So dot product with the normal in the numerator, the norm in the denominator. Yeah? Scales it by the area of sort of this cell, and then sums in a loop. Okay? And what you get is this matrix with 3 eigenvectors. One is the normal, and the 2 other ones are the principal curvature directions. And you can get the principal curvatures, you just got to be careful about those 3/8. Yeah? So this was the earliest curvature algorithm. And you guys will fill in some of the details on your homework. Harrison, you have a question or just an itch? Okay. What goes wrong with this algorithm? I mean, like in some sense it's okay, right? Like if I have a super fine mesh, this approximation does converge, right? Like this term vanishes. Notice that our meshes are nowhere close to being sampled in the regime where this thing kicks in. Yeah, I mean the models that I'm drawing you, right? Like this guy, that is not a Taylor series kind of mesh. Yeah, and in fact, that really is the problem. So when you run algorithms like this, I mean, essentially you're computing the curvature based just on some little pile of triangles adjacent to a vertex. And in some sense, that's all you should need, right? Like it's a derivative. You shouldn't need a big neighborhood to compute it. The problem is that that's noisy. If you're a signal processing person, you already knew that, because what happens to the Fourier content of a signal when I take its derivative? I amplify high frequencies. Yeah, which means that I need a really densely sampled thing because curvature is a second derivative object. Right? So the noisy part gets amplified when I differentiate. There are any number of ways to think about why this is a hard problem. But this is sort of the basic algorithm that's out there, and there are many different approaches. They all look something like this, where you collect some information in some ring of a vertex, you apply your favorite formula from differential geometry with a squiggly equal sign somewhere, and then out comes some approximation of curvature. And indeed, these are all perfectly reasonable models, so long as your meshes are extremely dense, right? And so the way I classify these is this is really engineering kind of disguised as math, right? You read these things and they have Taylor series and so on, but there are a lot of engineering decisions going into sort of what formula you chose. Yeah? And so the main takeaway so far, very similar to when we talked about curvature of discrete curves, is that you have kind of an interesting opportunity here, which is to use the application to motivate what curvature you want to measure, right? That just like in the discrete curve case, we're gonna find that you can't have curvature that preserves it all. Like, we proved a bunch of properties, right? And we're gonna show one more, which is the Gauss-Bonnet theorem. By show, I mean literally show, like it'll be appear on the screen in front of you, because it's a heavy one to prove. And essentially, we're not going to be able to come up with a discrete curvature that obeys all of them at the same time. Yeah? This is an example of one that obeys none of them at the same time, but we'll see that there are others that are approximations that do have some nice discrete structure. Okay? So we'll start our next lecture by talking about one other kind of heuristic example. Actually, do we have, technically this class ends at 4. We can do this in 1 minute or less. So this is another famous old paper on curvature computation on meshes. I don't think it's worth knowing the details because all of these things are more or less isomorphic to one another. So in their case, just to give you kind of a high-level idea of why these algorithms sort of all are the same and different, right? I mean, they all take formulas for curvature that agree to first order and then plug into one of them and then they're done, right? So in this case, they wrote out, this is Simon Ruzinkevich, writes out the second fundamental form of a surface in coordinates, right? So you really can think of it as a 2 by 2 matrix, right? It's literally dn dot v. I guess I forgot a minus, I'm sorry, my bad. And okay, so now let's say I take some other vector w and I write it in the same coordinates. If I want the directional derivative of the normal in the w direction, it's quite simple. I just multiply it by this matrix. Yeah. So what do? Well, they solve kind of a linear system of equations, right? They say, great. So let's say I'm on a triangle. I arbitrarily set up a UV coordinate system in the tangent plane. Turns out the choice doesn't matter here. And what do I know? Well, I know that if I take this unknown second fundamental form matrix and I multiply it by this edge, I should get something that roughly looks like the normal at this vertex minus the normal at that vertex. Again, notice I'm assuming I know the normal. So it's a pretty common assumption, but not necessarily a great one. By the way, we can get it by the mean curvature normal and get curvature for free at the same time. We'll come back to that. Okay, well, I know that for all 3 edges, yeah? And each of these relationships is actually 2 relationships because it's got 2 rows, yeah? So I have 6 different relationships, 4 unknowns in my matrix, so I can solve a least squares problem and get some estimate of the second fundamental form. And then I'm good. I take its eigenvalues as eigenvectors, that gives me curvature, and I have some approximation. In fact, in this paper, what they notice is that this is kind of noisy, right? It's constructing the form out of just like 3 data points. So they do something kind of tricky is they say, okay, I'm going to approximate here, but I'm going to actually say the second fundamental form I care about is on the vertices. So I'm just going to take all the fundamental forms adjacent to a vertex and average them together. And that has kind of a nice interference effect in some sense, right? Like it cancels out the noise of the adjacent triangles because you now have a bunch of edges all kind of conspiring to help you. And they find empirically that this gives you a pretty nice curvature tensor. Is it easy to prove theorems about this object? No. Does it give you nice, smooth curvatures? Yeah, in some sense you kind of smoothed it out just by virtue of averaging to triangles and vertices and back. And so in their case, they were concerned about these non-photorealistic rendering applications where you really want smooth curves and you care less if you get curvature right. And so for them, it made some sense. Yep. Or yet another one, there's Gaussian curvature and mean curvature you can get from a height function. So maybe you think of your surface as a height over some plane and you compute from there. There are many formulas out there. This was, for a long time, sort of an easy way to write a research paper in geometry. These days, if you do, you will be rejected unless you have something smart to say. Actually, that's true. There's one exception to that rule. Can anybody guess what it does? And then we'll call it for today. What would be the one way to get a paper with a boring topic published? I'm sorry, I shouldn't say that. Deep learning. Yeah, so they train a deep network to compute Gaussian and mean curvature on a surface, and depressingly, it works remarkably well. Okay, so in our next lecture, we'll talk about the sort of discrete differential geometry, conserved quantity approach to computing curvature, and then we're done with that. Then we'll start talking about geodesic distances and so on. Cool. All right, so we'll see you guys on Tuesday. Fabulous.